Can everyone see my screen? Okay, great. So I will talk a bit on this third edition of the Journal Club about face recognition, especially how much face recognition has improved through the use of margin-based loss functions. And recently, the advances on face recognition have been due to this kind of losses and not due to the increase of parameters in a model or the increase in the data set. So it's quite interesting to see how just small changes on losses can impact the performance so much. So I will present two papers here. The first one is the ArcFace paper. It's well known in the community, and it's also state of the art it was state of the art for the majority of the past years, but now it is not entirely state of the art, but is the base of most of the state of the art methods. And there is also elastic face. I chose elastic face because I believe it presents an interesting idea to improve ArcFace. I didn't choose elastic face as my first option because it wasn't already published on a conference or a journal, so it's still on archive. So then I will start by ArcFace. So during this presentation, I will talk a bit, give a small introduction about what is face recognition, about the elements that it requires in the entire pipeline, because face recognition is just a small part of a larger pipeline. And I will talk about some of the previous methods, mostly related to triplet loss and why there is problems and why we stopped using triplet loss. I will talk a bit afterwards then what is the additive angular margin that we will be talking about, and how can we further enhance it. So what is face recognition? Shortly, face recognition is a process of seeing someone's face and identifying the person. But you can do it in two ways. You can just receive the person face and then extract the features, process the information, and then decide if the person belongs, if that face belongs to a known identity or if you don't know the person at all. This is called identification. But you can also do verification, and verification is much more common nowadays. You basically, the person not only gives its biometric information like its face, but he also claims to be someone. And what we do is that we pick an image or a couple of images of that person that it's claiming to be, and then we compare the information, the two faces, and we verify if they belong to the same person or not. But what does it require? What is the pipeline for face recognition methods? So let's say we have a picture with a bunch of people, and the first problem here is how do we detect faces? So we basically try to do a process of face detection to pick at least one face from the image. Then to facilitate how this algorithm learns and to improve the results, it was found that aligning the face to have more or less the same structure in all the data sets was beneficial for the algorithm. So basically try that all the image in the data set have the eyes on the same positions, the mouth on the same positions, and we do this landmark alignment for all the image. And then we use a CNN to extract the features and get a feature embedding. So in detail, we have face detection that has a main goal of detecting the face on a larger image to crop the face and do a simple landmark detection, just the eyes, the mouth, the ears. And there are a few algorithms that can do this. MTCNN is one of the most used algorithms for this task. However, it does not achieve the best results. Currently, the best results are achieved with retina phase, but due to the enormous quantity of models that use MTCNN and data sets that are already pre-processed with MTCNN, researchers are having a bit of entropy when trying to change to retina phase. So there is, that's why MTCNN is still widely used. And afterwards, we do face alignment. We basically estimate a lot of landmarks in the face, much more than when we are detecting the face. And we use that landmark information to align the face. And it can be done in such a lightweight manner that it basically costs nothing in terms of computational power. So it's just a fine transformations on this part. Afterwards, we do feature extraction, and usually researchers tend to use ResNet, but not the ResNet that you are imagining, not the traditional ResNet. What researchers use is a modified version of ResNet known as iResNet. It's an improved version of ResNet. You can find the link below. And it tendentially has 50 or 100 layers. I believe that the traditional ResNet has not a 100 layers version, it's just 101. This one has a version with 100 layers exactly. And it includes in some of its versions squeeze and excitation blocks, achieves better results than traditional ResNet, and the feature vector is always fixed to be 512 dimensions. So while ResNet, the traditional ResNet, we increase the size of the number of layers, we also increase the size of the feature vector. For instance, ResNet 101 has a feature vector of 2048 dimensions. So afterwards, for the optimization of the network, for us for us to learn the weights, the appropriate weights, we can use Softmax, arc phase loss, and we can also try other different approaches based on metric learning, like triplet loss or contrastive loss. And well, let's start a bit about thinking about triplet loss, because it was the main method that tried to impose margins on this problem. So the idea behind triplet loss is not to do a traditional classification. We basically pick a triplet with an anchor and then a positive that is an image from the same person of the anchor, and a negative that is an image from a different person than the anchor. And what we try to do is while learning, is to optimize the network in order that the positive is closer to the anchor by a margin value that we give here as alpha, and that the negative is further away of the anchor, from the anchor. And this was quite a good idea, and it works quite well on the previous methods like FaceNet that was proposed by Google that learned end-to-end with triplet loss. However, triplet loss, as you can see here, has a problem. And let's say the network gets quite reasonable and it starts to learning more or less well. What happens is that in the majority of the triplets that we'll get, or of the batches of triplets, we'll be getting a lot of zeros. And the network will stop learning and improving because we'll be doomed by these zeros here. And even if the other triplets have errors, when we average the batch, we'll get a lot of zeros, and it will decrease significantly the gradients for the network optimization. And that's why triplet loss was more or less doomed across the years for face recognition. There is a solution for this problem. We can basically do online sampling or online mining of the triplets. This meaning we can pick an anchor and then carefully craft the positive and the negative in a way that we guarantee that they will have, if we do hard mining, we'll guarantee that they will be, the mask negative will be closer to the anchor than the masked positive. If we do soft hard mining, we'll ensure that at least if the masked is further away than the positive, it will still be at least within this margin value. In this way, we will not get zero gradients or zero loss, but it requires a lot of prep processing. And if the triplets are too hard, it will decrease the capacity of the network to optimize. It will be such an hard problem that the network will not optimize properly. But the idea that using this margin and trying to get close values for positive and anchors and further away values for negatives and anchor also supported the work of the angular margin based loss. So let's start by looking at what is softmax. When we use softmax and with cross entropy, we basically achieve something like this. This is an image from the ArcFace paper. The authors try to pick 8 different identities and the image from the face images from those identities, and optimize the network as a regular classification problem. So we have the network, we have the embedding, then we produce the classification layer, we run softmax on those neurons, and then we optimize with cross entropy. And we basically got this decision boundary. And while we can definitely characterize each phase here, there is some regions where the decision boundary gets mixed between the two identities. So basically, what authors proposed is to use, firstly, before the ArcFace paper, it was proposed to use this cosine loss or cos phase loss. So basically, what it does, I will explain later, but the idea here is that the last layer is only dependent on the cosine of the angle between the features and the weights of the network, of the last layer of the network. And what from this cos phase loss, what the authors of ArcFace propose is that we could add a margin to this value, to this angle between the features and the weights. And they did, and the results also improved here. So also just to note that the network is still trained with cross entropy, regardless of this activation on the last layer. So how do we do this in practice, and what is the visualization of what's happening on that equation? So basically, we get the features and the weights from the network. The features are produced by the convolutional part of the ResNet network that we talked previously, and we get an embedding with 512 dimensions. And we also have our classification weights that are normalized with the L2 norm. So both of them have a norm of 1. So here when we multiply them, we basically, or when we do their dot product, we are basically calculating the cosine of the angle between these two, this vector and this matrix. And we produce this vector here that is the cosine of the angle between both. Afterwards, since we want to, if we are talking about cos phase, we'll go directly from here to rescale the features, which means we'll multiply this cos of theta with a value s, that is our scale value. And then we'll produce softmax on top of that, and we'll just train with the regular cross entropy. With arc phase, what the authors proposed was that we could use arc cos to get the value of theta and then add a margin to that value. And after adding the margin, we can recalculate the cosine of that angle again and proceed to rescaling the features again and producing softmax. The idea here is that we can distribute the phases across the hypersphere and calculate the geodesic, geodesic distance between the centers of the faces. And the idea of normalizing here the features with a norm of 1 and normalizing the weights with the same norm is that the values produced will only be dependent on the angle between the features and the weights, and not be depending on any scale that could be here on the features or on the weights. So here the authors present the decision boundaries between softmax, sphere phase, cos phase, and arc phase, and it's possible to see that arc phase has a much linear, clear margin between two classes than, for instance, softmax, sphere phase, or cos phase. And while cos phase it's quite good at dividing and defining a decision boundary, this linear structure by arc phase has been proved useful in practice. So the authors also mention and do some brainstorming about the data sets that are in the literature, and they propose one data set. So basically they propose MS1 MV2, that is a fine-tuned version of a previous data set. Is basically the V2 stands for the second version of the data set that they propose, they clean, and they refine, and they show that is also beneficial for the algorithm. But since they are proposing a new method and a new data set, they present results on the method on the traditional data set, and then they present the results of the method on the new data set too. Here they also present the validation data set and the test data sets. It's also important to note that there is a huge difference between the number of image and identities between the validation data sets and the test data sets. The test data sets are much larger, and this ensures that the results are much more trustable and much more close to reality. So these ones here are used for quick validation, and these ones are usually defined that we use to compare different models. So they trained their model on Casia wave phase and present the results on 3 different validation data sets. And their results were quite above what was on the, in face recognition, when we say quite above, it's just a few decimals of percentual points. It's not a lot. I mean, but it's enough to show progress in the field. And they tried the value, their method with different scale values and different margin values, sorry. And they show that it has superior performance to other methods, even on different scale values. If we see, for instance, here ArcFace 0.45, it achieves state-of-the-art performance on this and this data set, well, not on this one. And ArcFace 0.5 achieves state-of-the-art performance on all the data sets. Afterwards, the authors decide, okay, Joe, so we showed that our method is superior, then let's train on our data set and show how it performs again. And they did. They trained a larger version, a ResNet 100 on the proposed data set MS1 MV2 with ArcFace, and they achieved results that are in some cases superior to human performance, and in all cases superior to previous methods. On LFW, they achieved it was the only case where they didn't surpass the human fusion performance, which means is the performance of several humans doing and fused in some manner to achieve this result, but they surpassed the performance of individual humans on all the data sets too. And they also compared a refined version of the IGB and IGC datasets on identification and verification, and they achieved state-of-the-art performance on all the cases with these datasets. With and without refinement, their model was superior to the performance, even when it was trained on Casia instead of being trained on MS1 MV2. They also shown again results, and this is more of the same. They try different architectures to show. Okay, so but is it possible to increase what these authors proposed? They tried to do this method that uses a scale, that uses a margin, but what if the margin was adaptive? What if the margin was not fixed? And so some authors proposed elastic phase, that is an improved version of ArcFace, that instead of using a fixed margin here, as we see, the elastic version of this loss basically samples from a Gaussian distribution with the mean, the previous margin, and with a standard deviation that is defined during training. And for each sample and for each iteration, a new value is estimated using this distribution here for the margin and here too. And what here we can see the representation. While on ArcFace the margin is fixed, on elastic phase the margin, well, while it tends to be here on the mean, it will vary between larger and smaller margin. And they have shown that the results also benefit from this change, because in some cases the network gets easier tasks, and in other cases it gets tougher tasks to learn. They also note if the standard deviation is 0, then we'll get the exact same results that with ArcFace, because it will be equal to be just M. They also compare their results with ArcFace in terms of distribution and the angles between the class. They get quite better results. here, and they also get better results on a different version of the model that they proposed, that is known as elastic phase plus. That what they do here is that they detect when the method is too close, when a phase is too far away from a center, they then try to increase the margin value so that it gets closer to the center. They here do a more specific analysis that is close to what is done, for instance, for the triplet mining of the triplet mining of triplet loss, and it improves the results significantly too. So also they use small values of standard deviation. So while the margin varies, it doesn't vary by a lot. So they also presented the results here, and they got state-of-the-art performance with, they did the same for cost phase and arc phase. They presented this change for both methods. And they achieved state-of-the-art performance in 3 out of 5 validation sets, and competitive results on the remaining 2. But on all the test data sets with a lot of data, except here in one scenario, they got state-of-the-art performance. And in some cases, it was by a large margin, especially when compared to the naive version of arc phase. For instance, here on IJBB, we get a significant bump in performance of more than 1 percentage point for the tar at far, when the far is fixed at 1 times 10 to the power of -4. Okay. So this sums up a bit what are these 2 models. And well, while I know that it couldn't be 100% clear about what both of those models do in practice, I will be open to questions, so I can try and clarify some misconception that might have stayed from this short presentation.
Shall I stop recording?